Welcome to Web Handling. My name is Dave Roysum. I am super excited to continue our Decades mini-series. In this short clip, we discuss super important web properties and how much they can vary in the wider web world. Properties we will consider include strength, stiffness, COF, and many others. Material property testing is also mentioned. I know your time is precious, so let's get started. Recall from the start of this mini-series, specifically Web20176e, how important web geometrical properties are. Length, width, thickness are almost always specified in converting contracts. Recall also how much they can vary in the wider web world. However, second only to these physical properties might be the most valued material property of all, namely strength. Specifically, ultimate strength, not yield or one of the many other strengths. That is almost certainly because it is easily defined and measured. Specifically, we mean MD strip tensile instead of CD. Finally, web handlers and almost all other groups use strip rather than grab tensils. The legacy of strength being the queen of properties goes back more than a century. The legality of strength is that it is often specified in converting contracts. Web handlers also treasure strength because it informs us of typical starting point guidelines for web tensioning, typically 10 to 25% of the web's MD strip tensile strength. We all have to choose units that make sense for our applications, and these units should be labeled every single time a number is presented, spoken or written. But here, I mean more than whether to express them in metric or US units. Rather, whether to use lineal tension, which is most common on machines, or full engineering stress, where we non-dimensionalize by both web width and web thickness. I choose engineering strength in megapascals or PSI because it avoids the wide variability of widths and thicknesses seen in the web world, which we already covered in Web 201.76b. If we non-dimensionalize by both width and thickness, we reduce the range from many orders of magnitude down to around 3. Here we see that steel is perhaps 1,000 times stronger than the weakest web that would include wet or perforated toilet tissue. Anything weaker cannot be tensioned and must be carried on forming belts. Most materials, including all paper and paper boards and most films, fall in the range of 10 to 100 megapascal strength range. Modulus is a measure of material stiffness. It can vary from stretchy, like a rubber band, to stiff, like steel. While modulus can be measured on similar equipment to tensile strength, it requires special software. Web handlers use modulus for at least 3 purposes. Researchers require it for modeling. Also, thick, stiff materials have minimum core and roller bend radii before web damage occurs. However, by far the most common use in web handling is to tell us whether we should use speed control or tension control or either. Rubbery materials are most easily handled under speed control, often improperly called draw control. Stiff materials are most easily handled with a dancer or load cell tension control. Materials in between might be handled either way. Modulus only varies by about a factor of 100 for common materials. Nylon, rubber, and some nonwovens are at the low end and metals at the very high end. Paper and most films fall in a rather narrow range of 1 to 5 gigapascals. There are many other strength-related properties that the web handlers might find handy. Modulus of rupture, sometimes called TEA or total energy absorption, combines the ideas of strength and modulus together. It is simply the area under the stress-strain curve. It is very predictive of web breaks, aka runnability. Another interesting property is Poisson ratio. That is a measure of necking. Solids typically have Poisson ratios of about 0.3, but they must have Poisson ratios between 0 and 0.5, which is incompressible materials such as rubber. However, structures are not so constrained. They can be less than 0, where the web actually gets wider when you pull on it, to as much as 3, where the web necks more than it elongates. I believe that friction is, by far, the most underappreciated material property in web handling. It is useful for many things, such as predicting web-to-roller traction for design purposes. The COF of most webs on metals is around 0.3, but on smooth rubber coverings can be more like 1. No less important is web-to-web COF because it informs us of what to expect for certain winding defects. PET is super slippery, and thus type 1 telescoping is thus anticipated. On the other extreme, certain webs have interlayer COFs exceeding 1, in which case out of round and vibrating wound rolls can be anticipated. We could go on and on with chapter-length descriptions of important web properties and how to test them and how to use them. However, there is simply no need. All you need to know for most of these purposes is to review Chapter 2 of the must-have 750-page Web Handling Handbook. I hope that you have enjoyed this episode on material properties in this Decades miniseries. Stay tuned for next week's show, where we will discuss the wide range of wrinkle-like behaviors. If you have a topic you would like to hear about, let me know in the comment section below. If you found anything interesting or useful here, please like and share and subscribe. See you next time.